Restoring a lathe isn't just about making it work. It's about chasing precision far beyond what's strictly necessary. Leveling the bed, aligning the headstock, dialing the tailstock. Each step brings us closer to a machine that not only works, but works right. We may never reach perfection, but in the pursuit, we refine more than the lathe. We refine ourselves.
Hey, welcome back for the part 2. If you missed the first part, please go see it, it will give you a better context. Last time, after we reground the spindle taper and changed all the headstock bearings, just when I thought that we're done, I discovered that the spindle lubrication was not working. In this video, we'll address just that, then align the headstock, do some changes that we can call LikeFactoryMade, then put it all together, do some test cuts and see where we are. This project took about 6 months and these 2 videos were distilled from 18 hours of raw footage. If you're into this kind of deep dive, please subscribe, hit the notification bell so you don't miss what's coming. Let's begin.
Just when I thought that all that's left to do is to align the headstock, I need to take it off once again. So, time to drain the oil. Again. The spindle bearings get lubricated by the oil that gets splashed into this pan, and this splashing is kinda dependent on the spindle speed. This can't remain like that. Not when I've sold a kidney for a brand new set of precision spindle bearings. The larger WeilerE E-series models, like the E50 my friend owns, are using an external pump for spindle lubrication. Exactly the setup I'm aiming for. However, the E50 has a separate oil reservoir and a pump that runs continuously while the machine is on. In our case, we'll use the existing reservoir, so we need to take the headstock off and drill 2 holes. One for drawing out the oil and another one for returning it back in. Something as simple as drilling and tapping 2 holes feels pretty stressful right now. I've already installed the new bearings and dialed the preload perfectly, so the idea of pulling out the spindle again doesn't sit well with me. But what really worries me is the cast iron dust. It could settle inside the headstock and eventually make its way into the new bearings. So in order to prevent that, I calculated the position of the holes, then stacked inside the headstock all the neodymium magnets I could find in my shop. I hope that combining this solution with dust extraction from the outside should keep me on the safe side. I got this pump from a friend. On the initial test, it seems to work fine, so I'm trying to see how to integrate it here. Check out the clamping on this side. I was too lazy to take the offset, so I eyeballed it and set the coordinates of the first hole as XY0. Then, for the next one, set it to 80 mm away from the first one. Since I did not have the correct drill size for a 1/4 of an inch pipe thread, I made the program in Fusion with a boring toolpath and a flat face for a copper washer. But when I made the CAD, I forgot the most important aspect. To set the 80 mm distance between the holes. By default, it was some 80 something. I noticed right on time not to break the end mill. Yet. I was too lazy to go back to the PC, update the program, repost it, so I thought I can just work around it. So, I've set the coordinate at this hole as the new X0 and rerun the same program. And completely forgot that my program tries to work on 2 holes. And this is how you kill a brand new carbide end mill. But it's not the end mill I was most upset about. It was the fact that I've left this mark. After patching up my pride and ego, I realigned the headstock and tapped the holes. To keep the dust out, I plugged them while drilling and tapping a few blind holes for the pump's mounting plate. With that bearing threatening operation out of the way, it was time to see how well my magnets held up. And it looks like they did their job. Did you miss a side project? There we have one. As someone pointed out, just like inheritance machining, I should really have a side project counter. By November 2024, time was running out and one of the events I've been eagerly waiting was just around the corner. And for that, I needed to fix this power scraper. This one was missing the power button, but luckily with a TIG rod properly bent and a 3D printer I was able to get it fixed. With the power button finally working, after this warm-up I was finally ready for the scraping course in Austria. To prepare, I dismantled the lathe cross slide, built a support for the apron so that I could take the saddle with me as a case study. So when the course finally came, I was buzzing with excitement. I'd wake up 1 hour before my alarm, too eager to sleep, just looking forward to the day ahead. I can't remember the last time I felt that way, but I'm glad that spark is still alive in me. It was a week packed with theory and hands-on practice. I've made plenty of cast iron dust and ended up with some of my best prints yet. I also met a bunch of like-minded people who share the same passion and drive, and I truly enjoyed watching their progress on their own projects. Honestly, I doubt this machine ever looked this good when it left the factory. My friend David is a genius. He is my new wannabe in terms of hand scraping.
The man, the legend.
As for the precision, let me show you something that blew me away.
Did you take a video from
Yes.
punching here?
So now you're heating it up, right?
10 or 15 seconds.
That much? What the fuck? What the fuck? No way.
10 seconds.
And it seems to be moving.
Yeah, it goes back.
Oh my god.
This is exactly why the temperature matters when it comes to precision. Unfortunately, the guy who reground my saddle did not know or did not care about details like this. He skipped addressing the wheel before the finishing pass, so he ended up rubbing more than cutting, building up heat and expanding slightly. It's off just by 10-15 microns, but one day it will be spot on. Once I'm back home and burned through a few hundred hours of hands-on learning, I'll rescrape it to the same standard as my friend David's work. After a week of learning and hands-on work, with this paper in hand, I finally felt confident enough to start scraping the base of my headstock and continue the alignment process. While I was in Austria, I spoke with the Luftinger brothers, the guy who ran the scraping course at Mascheratur and professional machinery builders. I asked them how they would approach a situation like mine. Their advice was pretty much the same as what I got from Stefan Gotteswinter. First, I should scrape the flat portions of the way to make sure there are contact points across the whole surface. Since the headstock fully assembled with all its gears weighs as much as I do, the headstock swinger is absolutely invaluable. Matching two surfaces by scraping is an extremely time-consuming process. Dealing with that much weight makes it even more difficult and a bit dangerous. I ended up spending a few late nights going through the scrape blue cycles, and without the proper setup, there was no way I could have done it all by myself. Since we have two parallel surfaces and we cannot check for pivot points, we need to scrape just the middle so that we keep the contact points only where the screws are. This way we ensure that if there is a rocking motion in the middle, I would not put tension when I'm bolting it to the bed. At this point we got the blue spot concentrated around the mounting holes to help distribute the clamping force from the screws when this gets bolted to the bed. Before I can put any oil in the headstock, I need to glue in place the plug that will act as a pivot point for the headstock. And I'm glad that I've managed to fix the hole for the pivot pin so that it's finally perpendicular. The oil pump that I had in mind when I drilled these two holes turned out to be not up to the task. It had an internal magnetic clutch that started slipping because of cavitation. As you can tell, I also picked up a new term along the way. I've changed the design a bit and bought a dedicated 24-volt oil pump. I also gave up on the mounting holes I drilled in the headstock and decided to get it mounted on the substructure of the bed, along with a support for an oil filter so that I don't push back any impurities. I am not yet ready for the final bolt down, but I need to put it back together and hopefully be able to align it just good enough so that I can turn a critical part on which I can't trust others anymore to do it right. For that turning operation, it was critical to have the spindle bearings lubrication working correctly. This is how the external lubrication will work. The oil will be sucked through this port, enter the pump, and then from the pump into the filter. Then back into the headstock, where through a hydraulic pipe it will go into the oil pan, filling it independently of the spindle speed. It will run for 3 seconds every 30 minutes. After a bit of headstock alignment, I was ready for the first turning with the new bearings. And by a bit I mean... From a timing perspective, my friend decided to order the ball screws without the ends pre-machined. So I took the risk and decided to machine the one for the X-axis myself. Using the steady rest, I managed to center it within 100 of a millimeter. I needed to make sure that the center of the holes were as perfectly aligned with the nut as possible for the upcoming cylindrical grinding. Off camera, I did the rough turning and managed to stay within 100 of a millimeter. This ball screw turning detour was needed because I had to take this to the cylindrical grinding. Now that the other hole is spot on, I can resume working on the latest sheet metal parts that I received from my friend Horia. I've redesigned the cable duct, made it a bit wider and added some slots in the bottom so that I can zip tie the cables. I just need to add some filler materials into the corners to give it some strength. The differences compared to the previous one are subtle, but when chasing perfection, the details matter. Rerouting the cables also meant modifying the apron cover. I wanted to reuse the old handwheel mounting rings, so I wrote a program to cut off the welds and get them out. But more on the sheet metal changes once everything is painted and we can start the final assembly. For now, let's get back to the headstock. As you can see, we took it off again. Hopefully this is the last time. It looks like the vertical alignment came out just right on the first try, so no more scraping is needed. Now we can prepare for injecting the epoxy under the headstock. To keep the epoxy confined to the V-ways, I'm sealing the surface with double-sided tape and some foam strip I had laying around. And a thin film of wax in case we ever need to take it off again in the future. Hopefully, this is the last time I ever hear the sound of the chain hoist near to this machine. When the foam compresses, it will keep the epoxy confined between the surfaces. For the open section of the front E-way, I'll add the wooden strip during the injection. As I mentioned earlier, the vertical alignment is good, so for now I'll just lightly torque the screws so that we can still beat it into submission horizontally. Let's see what we've done. The inner taper was not perfectly ground, but with about 400 of a millimeter I averaged it out. I think we're ready for a test cut. The headstock is now aligned and ready to receive its epoxy. The powder coated sheet metal is back, scattered all over the shop. My workbench is full with lathe parts. After 6 months without a working lathe, it's time to reassemble. Long before the scraping course, I scraped the saddle so only the ends make contact with the bed, and also improved the oiling grooves. Now that I know more about scraping, I'm not too happy with how this looks. But after some more practice, this will come off again. Considering that I improved the lubrication and I have a very light use in my shop, I think it will survive until I'm more confident with scraping. The main reason this lathe ended up with a reground bed was a faulty lubrication line, so I tried to pay extra attention on this aspect. On the closing plate I even added some recess for an O-ring, then milled some oil groove onto the contact surface. Same for the back closing plate. The back closing plate now also holds this new aluminum part, the support for the reed head of the linear scale. And of course, even if it's not very exposed here in the back, I could not call this LikeFactoryMade without a proper glass scale cover. In the last 6 months, the apron has spent more time being on my workbench than on the lathe. So it's time to finally put it back where it belongs. Just from the weight of the apron, I can already feel that the saddle needs more force to move and it has more inertia too. So now is the right time to fill up the oil lines and hook them up to the meter valves. These valves deliver a set amount of oil to each point, but as an improvement I increase the oil flow for the front and back ways. The next few minutes are quite self-explanatory, so just relax and enjoy the process. This is the last moment the old and the new ball screw will be side by side. Time to install the new one. If the old one survived 30 years of industrial use, it will definitely outlast me. Now that we got this new apron cover painted, it's time to mount back what makes this lathe really powerful. These hand wheels are what differentiates this machine from a regular CNC lathe. Most of the time when you want to do prototyping work, a manual machine is much faster, but when you want to do repeatable work, a CNC lathe is way superior. These hand wheels are what makes a CNC lathe a great prototyping lathe, where you can get the best of both worlds. And talking about prototyping, as a support for the linear scale of the X-axis, I've went through 3 different designs until I found the best match for my ideas. The last design has another function. It will carry the coolant from the back of the slide to the front of the slide without stealing any space from somewhere else. I've drilled and tapped some intersecting holes that will be plugged later. Then, since I did not have the drill long enough, I cut a groove for a glued-in hydraulic pipe to carry the coolant from the back of the slide to the front of the slide. With the linear scale support mounted, it's time to attach the razor for the reading head of this 0.5 micron linear scale. This should give me a resolution of 1 micron per diameter. And before tightening the screws of the linear scale, indicate the bottom of it to make sure it's on the same height across all its length. As you also may have noticed for the Z-axis, I've shortened the cable for the linear scales so that, if needed, I can quickly disconnect them from the back of the slide. Oh, you have no idea how long I've been waiting to put these sheet metal covers back on. Even if it was a project I wanted to make, the feeling of completion is something you can't beat. In the original design, this sheet metal cap was painted and set just below the slide height. Since I always ended up placing tool holders on it, I remade it from stainless steel and even added the round milling to match the way cover band radius. This limit switch from the saddle should stop the Z plus motion if it encounters the tailstock, but since the tailstock is moved manually, we need to prevent crashing it into the linear scale. This M6 screw will do just that. Regarding the coolant fitting, when the X slide is moved at its max travel towards X+, we still have a safety gap of 0.15 mm. And now, time for adding the rest of the sheet metal covers. The way cover that you see is doing its job well for over a year now. The video in which I've built this was one of my most popular, with lots of comments, even from cool YouTubers like Stefan Gotteswinter or Blondie Hacks. If it sparked your interest, click on the info that appeared on the screen and check it out after this video. After 6 months of having just parts of a lathe, but not actually having a lathe, the moment where I can finally put back on this tray marks the end of a journey. We started the first part of this rebuild video by turning a test bar. Now, after all this effort, it's time to check the results. We're not shooting for a certain diameter, we only care about how close these two diameters are. Upon multiple readings, the smallest reading I've got is 56.249. Let's see how close is the second one. 56.249. It seems we're spot on. If my measurements are correct, we're 10 times below what's accepted by the factory.
If you watch this video carefully, you may have noticed a few things missing. First of them, I have not injected yet epoxy under the headstock. I have not done that yet, as I was not sure if my tests are correct, and once I inject the epoxy, it's too late for any changes. I'm not a professional machinist, I'm a self-taught guy, so if in this process you notice something off, something that is not right, a measurement that I've not done correctly, please let me know in the comments. If I inject the epoxy, it will be too late, so hit me up with your feedback.
The second thing missing are the backlash measurements, but do we have any backlash with half-micron linear scales?
The linear scales are not hooked up yet, even if they're mounted. The electrical cabinet looks like this, is still work in progress. The linear scales are coming here, but are not going anywhere yet. All this will be done in a future video when I have time to do enough R&D for all this process. If you enjoyed this video, please subscribe and hit the notification bell so that you don't miss the next updates about this machine.